Let us start with a program for the largest of three input. So this is the logical diagram which we want to implement in the LMC program for finding out which one is the largest out of the three inputs given. So first of all, we take the input A, input B, and input C. Then we check which one is the largest. For example, if both the values which I subtract from each other, if the C is larger than B, then the value will be positive. If the B is larger than C, then the value will be negative. So this is a good check to find out if B is larger or C is larger. So if C minus B is positive, means C is larger. Now C is larger, but we have to also find out whether it is larger than A. So the second test we have to do is C minus A is also positive. If it is positive, the C is largest. But if it is negative, that means the A is largest. The other way around, consider the very first condition false, and then B is larger because the value is not positive. In that case, again, we need to check whether A is largest or B. So for that reason, we are again doing the same thing. B minus A, we test if it is positive, the B is largest. But if it is negative, means A is largest, and then we give out. So the green box indicates always the output, the blue box the conditional check, and the black box as an input. Now, we want to implement this logic. It looks complex, but if we subdivide it into the three phases, like first section as input, the last section as output, and the middle section as logic, it will be modularized and the complexity will reduce. Also, we should learn this time the symbolic addressing. So let us start. Now in this program, we are trying to code the modularized section. So for that, let me write down here, program to find out the largest of three numbers. So for this, I divide the section into input, logic, output, and the data. So obviously the data section starts only after the whole. Now in the data section, because we are taking the three input, we would like to store the data. We consider the symbolic addressing. Now what is symbolic addressing? Instead of remembering the address value, we would like to give a label which we want to refer as a data, so that now and then frequently we can access those locations by means of label. And we mention it as symbolic addressing. For example, I give a label A to this data where I'm initializing it with 0 so that I can frequently refer this to store and access the values. So I have defined three labels, A, B, and C. So instead of remembering 1, 2, and 3 as the address values, I will be actually referring A, B, and C. And so I don't have to worry if my line number changes, my address number does not change, or it doesn't matter even if it changes because I'm referring always the labels. Now, first and foremost thing I will start with is input. So let me take first of all input. the first input, I store it as A. So now you see how I access these labels. When I access A, the control comes here, gets stored here. Then we take the second input, store B, and then we take the third input, store C. We have taken the input, we have considered the data part. Now we first of all code the output, and then we'll go for the complex part called logic. So for output, it's very clear, whichever is the largest, we have to load that, we have to out, and then we stop the execution. So for that, I would say A is largest. So I label it, and then I give it load A, so that anytime I find out that A is largest, I have to just transfer the control to AL. It will load A, it will output it, and then the execution stops. Therefore out, and then what? Then I have the second input, maybe the B is largest. So load B, out, and halt. And suppose C is largest, load C, out, and hold is over here. So we have also written the output. So now you can see that we have coded this section of input and this section of output. Now we are just worried for this. So once we take the input, we know that our accumulator has C, and then we test first of all C minus B. So C is already in the register, so we have to just write sub B and then BRP for checking whether it is positive or no. If it is, then we will do something for the next check. So let's implement that one. So in the logic, what we need to do is we subtract B. And then we check BRP. If it is, then C is big, but not the largest, right? So it's not largest. Why? Because still A need to be checked. So for that, I will go down, and then C is big. And what I need to do is I need to load C and then test for the second condition that is here. So now the accumulator has, as of now, C minus B, right? This is what we did last time. So this is what is in the accumulator. Therefore, we need to load C, sub A, and then again check if it is positive. So load C, sub A, and then if BRP means branch in positive, if the value is positive, then C is largest, right? Otherwise, means if this statement is not executed, means else part is come, means this whole computation of C minus A is not positive. That means A is largest, right? Therefore, branch in unconditionally, A is largest. Now this A is largest is actually here already getting executed as a next line, right? So overall, if you think this line is not necessary because the next line itself is where you are jumping. So we'll check about it, but logically it is correct. So just now I'm just writing not necessary, but logically correct. So we'll try to remove this later. But logically, we have covered so far this condition and this condition. And we are handling this as an output and this as an output. But we haven't handled this condition and this side of the tree. So for left tree, we need to go back and we should start coding here. Because this is where the control transferred and then we started coding that section, right? Now we come back. Suppose this is not true, means this condition is false. Then we need to check this. So let us start with load B because we want to do B minus A, right? So load B sub A, and then if that is positive, right? So BRP, if that is positive, B is largest. If this is not true, means the control will come here. That means the A is largest. So branch unconditionally and A is largest. Thereafter, we have this section coming up. So control will go to the A is largest. So the control comes here, gets executed, gives output, and the program stops. So this is how our logic is written. So we always know that to reduce the complexity, first of all, you handle the input and the output section. After that, fix the data section, which is always after the hold, so you can also manage it very well. The symbolic address is a boon. You don't have to worry about the exact values of the address. And then if you perform the logical conditional check, it will help you. Now let us test if all the three input gives us the correct answer. So I'm running it. You can run it by entering F5 or function F5, right? So that's a shortcut. So it is asking me for input. Now you can see there are 0 values here, but it will be replaced once I give the values. And this is what is the logic. Now here, whatever comment we give near the statement, it gets written in the comment section. So you can use it if you want to write something as a logical comments for your reference in the later stage. Let us consider that the C is largest, because first and foremost thing we want to test is if C is largest, right? So for that reason, what we are doing is first we are giving the A value as 10. The B value I'm giving as 20. And then C value is which is largest. So that is 30. So the output should be 30, right? And see, all of them are here. And yes, the output is 30. So this tree is working fine. Now let us see if this tree is also working fine, right? So we want the C minus B to be the largest, but also this side. So A should be larger, right, than C. And B should be smaller than C, right? So let's run it. So B should be smaller than C. So A should be larger, so I'm giving it 30. B should be smaller, so I'm giving it 10. And C should be 20 because B is smaller than C. Then only this tree will be executed, right? And it should give me 30 again. Yes, though A is, so this tree is working fine. So this side of the tree is tested, it's working fine. Now let us see this side of the tree. Now B is larger than C, but smaller than A. Then A is largest. If B is larger than C, but bigger than A, then B is largest. So let us try both this input. Now A is smaller, B is larger than C. There, C. Now it should give me 30 as an output. And this proves that this side of the tree is executed correctly. Now only option is this one. So A is largest, but B is larger than C. So therefore, A is largest and B is larger than C. And it should give us 30 as an output. Yeah, so all the 4 trees we have tested, and logically it is identifying the things. So this is how we code the largest of 3 inputs with the logical implementation on LMC.